Hello, KubeCon. Hope you all are having a great start to your week. My name's Dom Del Nano. I'm CEO and founder of Cosmic and also a CNCF Pixie core maintainer. And I'm excited to talk to you about expanding eBPF's reach. So before we jump into things, I wanted to give myself a brief introduction. As I mentioned, I work on the CNCF Pixie project. I got started back with the project 3.5 years ago, first as an end user and then turned maintainer. I also spent a bit of time at CrowdStrike working on their eBPF Linux sensor, so I've been working in the eBPF space the last few years. So before we get into the eBPF stuff, I wanted to talk about where things came from. So before the cloud and containers, we had these monolithic architectures. They were simplistic. It was easy to debug issues. These 3 pillars of observability weren't really a thing at this point because inspecting and finding bugs were easy. They were in the big monolithic application. And so it wasn't until microservices and containers and Kubernetes came along that observability became a really important operational tool. And so you can see on this picture here that these are what our environments look like today. We have services written in different programming languages. We have SaaS services. We depend on all these third-party APIs that we have to talk to over the internet. And also, there's a variety of data stores used. And so observing these things becomes very important when there's so many different logical pieces. And monitoring and observability started off with manual instrumentation. So back when there was the monolith or less programming languages, it was easy to instrument each piece. But as the number of combinations grew, it became a lot more effort and work to support Go, to support Java, to support all these different flavors of things. And so this manual instrumentation started to become very expensive in these polyglot environments. This is where eBPF comes into the picture. So we're going to kind of compare how you would traditionally do monitoring observability against how auto-telemetry works. And so there's sort of 3 verticals to think about. There's coverage, effort, and flexibility. So for the manual instrumentation, the coverage tends to be sparse. For third-party applications and SaaS, it's often infeasible. Unless you can change the code, you can't instrument it. Or for SaaS tools, you're talking to it over the internet, and so you have no control there unless they provide an interface. It also tends to be inconsistent as you have more programming languages and tools you have to support. Comparing that to the eBPF case, the coverage tends to be very broad. Because eBPF hooks in at the kernel level, you have system-wide view. And actually, this even allows you to introspect things like using SaaS services, because eBPF instrumentation can hook into TLS libraries, and so you can see the plain text of encrypted connections. So you get this language and framework agnostic view into your system. Moving on to effort, as we mentioned, the manual instrumentation is expensive. If you have X number of languages, you also have to instrument that X number of times. With eBPF, the instrumentation cost goes down dramatically because hooking into the kernel, you instrument it once, and it's already available. And the final thing is flexibility. This is actually a benefit to manual instrumentation. Because you're making the change, you get to decide how it works. For eBPF, it's tooling dependent. So it can be flexible, but it also, because it's automatic, could be inflexible. And so that's something we're going to dig into today with, as you decide on which eBPF tools to use, determining how flexible a given tool is very important to make sure it works for your use case. So just because you have the coverage that you need doesn't mean that you're going to automatically have debuggable systems. Auto-telemetry gives you access to more data because you're not opting into things on a case-by-case basis. And so observability data, which is notoriously high volume, low value, often becomes a little bit more painful because you now all of a sudden have even more data because it's this high volume data source. And so you have to make sure that you don't obscure important system signals as you have access to more telemetry. And so with that in mind, as I was putting together this talk, Bill Mulligan, who is a community manager for the Cilium umbrella projects, made a post about how you make eBPF impactful. And so, like we just mentioned, eBPF can be a fire hose. The real value lies in the aggregation, analysis, and actions from the data. And so users don't want just a wealth of information. They want insights. They want to know what they have to act and do. And so impactful eBPF tools aren't data collection just tools. They actually roll up and provide you the important signals that you need. And so as we go through this talk, we're actually going to look at this and decide how you evaluate eBPF tools to make sure that they can provide these insights for you. Now, unless you're an eBPF developer, I recommend that you stick to these higher level projects that provide these for you. And so these three properties that we talk about are going to be the way that you evaluate these projects. So in order to tame this fire hose of data, an eBPF tool needs these three things. The first is data enrichment. eBPF is an extremely low-level data source. An example of this is it often traces network traffic, which is like bytes on the wire. But that's not helpful for debugging microservice environments. You actually need environment context to debug your systems. And so these tools need to enrich your data with Kubernetes primitives, with container primitives, in order to make it useful. The second is that because auto-telemetry is done on your behalf, you need to have more flexibility built in. And the first part of that is it having structured APIs. You need to be able to get the data out of the system and also be able to do any filtering or other things that you need to do. Oftentimes, you're going to want to use this data for your own, you're going to have a different view or scope that you want to look at, and having these structured APIs makes that possible. And the final property that we'll talk about is programmability. And I summarize this as domain-specific extensibility and processing. If you're using eBPF is applicable in security contexts, in observability contexts, and you need the eBPF tool to not just filter the data, but you actually want to be able to apply observability focus on it or security focus. And I think this will become more concrete once we look at some examples. So yeah, we're gonna basically walk through 4 different projects and view them in light of those 3 properties that we talked about. So the first is Inspektor Gadget. An Inspektor Gadget is an observability tool that packages eBPF program into these concrete chunks called gadgets. And they basically manage the deployment and execution, and so you can run them across your cluster. And there's a variety of out-of-the-box gadgets that you can use, so you can view network traffic, trace processes, all of that stuff. And it really is a full observability framework. It's container and Kubernetes aware, and it provides rich filtering, collection, and the ability to export it to other systems. Next, we'll move on to Pulsar, which this is the only security project out of these 4. But what Pulsar is a runtime security tool. And what it provides is it taps into these file system, networking, and syscall events through eBPF, and it routes them into this event bus that it has, and you define these rules that the rule engine will then evaluate, and it'll decide if a given set of events is something that you deemed a threat, and it'll notify you if needed. Next, we'll move on to Pixie, which, as I mentioned, is the project I work on. Pixie provides protocol tracing, which you can see from this HTTP service map. You can get a very nice high-level view of how all your microservices are connected. It also provides resource utilization, so you can get like a per service dashboard that shows you CPU, request latency, memory use, and we also do CPU flame graphs, so you can debug where your performance issues are. And finally, we have Hubble. Hubble is the observability part of the Cilium project, and it provides you with service maps so you can see how all your services are connected, and also gives you deeper inspection into layer 4 and layer 7 events. An example of that is this Hubble observe command, which is asking for the last minute of layer 7 events, and it's filtering down for anything that has a DNS R code equal to 3, which for those who aren't familiar is NX domain, or the signal that your domain name does not exist. And so this is indicating that this Star Wars service is not able to connect to whatever its dependencies are and needs more investigation. All right, so now that we've gotten a brief introduction to all of these projects, we are now going to go back to our properties and point out how these projects accomplish these important primitives. So first of that is the data enrichment. We're going to look at Inspektor, Gadget, and Pixie. On the left-hand side here, we are looking at the trace DNS gadget, which shows you all of your DNS traffic. Now, it's worth mentioning, I mentioned unless you're really interested in peeking behind the curtain or really tuning and writing these eBPF tools, you don't have to go this deep to use these, but we're going to find out what their special sauce is. And so for Inspektor Gadget on lines 5 and 6, this define statement and the include statement, those are the two things that Inspektor Gadget provides that then automatically enriches the eBPF data with container information. And so it's very easy for this to just automatically take this low-level kernel information and populate it with that rich application-level context. Moving on to the Pixie side, we're also looking at something that can view all of the DNS traffic in the cluster. Pixie has this Python-like language, and so we're querying all the DNS events. And then on lines 7 and 8, we are basically accessing the pod associated with each event, and then we're also doing an IP to pod name lookup on the remote address side. And then just to get a full picture of what this looks like, if we look towards the bottom of the slide, we have an example of what the output of the trace DNS gadget is. We can see there's the Kubernetes namespace and Kubernetes pod name. And similarly for the Pixie command, we also see that there is the pod. And then in the case of the source column, it happens to be localhost, which doesn't map to a pod name, but all of that rich enrichment is there. Moving on to the next property is structured APIs. And so looking into Hubble a little bit more, Hubble contains this component called Hubble Relay, which provides access to its network flow data and exposes it over a gRPC API. The Hubble UI and Hubble CLI actually are built on these components, so they basically dog food this interface, but it's also exposed if you need to power some other custom integration. Maybe the Hubble UI, you don't want a service map, but you want something different, and the Hubble CLI isn't the right interface. You can build on top of this on a very high-level interface easily. It's also worth mentioning that even though I'm only highlighting 2 projects for each of these properties, for data enrichment and structured APIs, all of the 4 projects we are talking about today all fulfill that interface. And then moving on to Pixie. So Pixie's structured API is its pixel language. It's what we saw on the other slide, that Python-like representation. And so basically you get Python/pandas processing for your observability. And so you get this data flow programming. And similarly to the Hubble case, Pixie's UI is built entirely on Pixel. And so you can actually change your Pixel code, and that will change the visualizations within Pixie. And similarly, the CLI also uses Pixel in order to do its data access. And then if you want to build any third-party integrations, we expose client libraries, and Pixel is the input to those as well. So, these three things feed the Pixie API, the Pixel script. It does the processing and data filtering, and back out, you get your metrics, spans, profiles, and events. All right, and on to the final principle, programmability. And what I want to mention is programmability of these 4 projects, Pulsar and Pixie, are sort of unique in that this is sort of like a much harder thing to fulfill. And Pulsar, being a runtime security project, it has this rich interface to define what security policies you're interested in. We can see from this snippet of code down below, we have 2 rules. One of them is looking for sensitive file access. And so any process other than SSHD, if it is accessing the etc shadow file, that is going to be flagged as a threat because it's unexpected and you need to understand better why that's happening. And similarly, if you have, in this case, telnet or using netcat is considered suspicious activity, you probably don't want people telnet is an insecure protocol, and for netcat, you don't want to be kind of exposing any, listening sockets. And so these 2 rules here would allow you to take, the security principles and rules that you want to enforce and distill them into this framework. And so the programmability is really about, we're in this security domain where we need to have this rich filtering and triggering of events, and Pulsar basically maps that very well so that you as the end user don't need to take on that complexity. Moving on to Pixie. So this Pixel script should look familiar. The additional lines that we're looking at here are lines 10 through 12. And so in this case, we have this, we're basically detecting if the destination pod failed to look up. Like, let's say the IP was an internet address, there's not going to be a pod name associated with that. And so Pixie has this NS lookup function, which allows us to turn an IP address into a domain name. And so what this allows us to do is, if we look at the bottom of this slide, there's basically the table representation of this output. And so in this case, we had a curl command running in this bash pod making requests to the Stripe API. And so the destination pod column, or the remote address, was this internet IP address, which we didn't know anything about. But the NS lookup command allowed us to turn that into the actual host name. And so very quickly, we're able to see that this is making an outbound connection and exactly what it's accessing. And so similarly to how Pulsar models the security domain really well, when you're debugging systems and trying to understand your system's behavior from an observability standpoint, this type of programmatic functionality is extremely powerful. And so, like I said before, this programmability is a really key extension to make these eBPF tools really, really powerful. And with that, we are going to watch a demo. And this is going to give us just a little bit more detail into the 3 pillars and specifically how Pixie showcases them.
Now that we've learned about the 3 properties that make eBPF tools really powerful, let's look at a more in-depth, hands-on example with Pixie with some new functionality that's coming soon. So as we talked about before, data enrichment is very important, and Pixie has relevant Kubernetes metadata. We can see from the service map here that all of these refer to Kubernetes service and deployment names, and so the data is very rich to begin with. As we mentioned, Pixel is basically the API, and so all of this visualization is defined by this Python code. Now, moving on to that final programmability principle, we're going to look at a case where Pixie is going to ingest a new data type. So currently, Pixie supports BPF trace. If you're not familiar, it's a command line BPF tool, but its only really scope is basically a single instance. And so what this script does is it basically checks to see if the operating system or Kubernetes has issued any kills. And as you can see here, we do have an application that's ooming. I deployed something to this cluster ahead of time that is constantly allocating too much memory, and so we're constantly generating these events. Now, debugging kills, you have to have a lot of other system context there. And so wouldn't it be great if not only in addition to these events, what if we could grab the syslog output from the last 5 minutes and basically batch these eBPF events with the syslog data? Well, that's what we're just about to do. So I have created a new Pixel script that essentially takes these two data sources and combines them together. So that kill BPF trace script that we already saw, that's basically we're embedding the same code from that other script. The new piece here is that Pixie now has the ability to basically tail log files and turn them into our data frame representations. And so what this script is going to do is essentially when there's an kill match, it's going to merge these two data frames together. And so we're going to get the timestamp that the kill happened, the process ID that was killed, the command itself, and also the syslog lines that were with it. And then we're going to send this off to OTel export. So in addition to that, there is this new visualization that allows us to view kind of Pixie's processing of this data called pipeline flow. And so what we can see here is Pixie is currently ingesting HTTP events and data from syslog and also these kill tracers, and they're flowing through the data collectors, through Pixie's aggregator node, and ultimately out the OTel export, and also some visualization, like kind of from the UI. But so what you can see here is that we are seeing kills flowing from this single PEM, whereas the other one, there is no data flowing. And that's because this crasher pod is only running on one instance. And so right here at a very high level, we can see basically Pixie's programmability in action, the eBPF data, the data from the files, and also the kill data from BPF trace flowing through the system and out through the OTel export.
All right, so there we kind of see Pixie. One second. There we see how Pixie kind of combines all three of these eBPF properties to make it an extremely flexible tool. And this is how we go from auto-instrumentation to observability pipelines. By Pixie being able to now process files, and also having that edge or agent to aggregator to export architecture, it puts it in line with tools like Fluentbit and Vector, where you can actually do processing at the agent level, processing at the aggregator level, and ultimately to your sink. And that allows us to do this correlation between the kills from eBPF and attaching the other system behavior from syslog. And so to wrap things up, the high-level points are automatic instrumentation is easy. You want your eBPF tools to provide insight and have really great tooling, and that's what's going to give you value in being able to solve your debugging and other system problems. I want to mention again that unless you're an eBPF developer, you probably want to reach for these tools because that will be the fastest way for you to get to these insights. And then also, I just want to reiterate that just as you evaluate eBPF tools, you want to keep these 3 properties in mind to make sure you get the insights you need: the data enrichment, structured APIs, and programmability. And with that, I want to thank you all for attending the talk, and I'm happy to stick around and answer any questions that you have.